far what we did in the morning? Okay, so let me ask a simple question now. We've been looking at all these sampling patterns here, right? We saw all of these things. And this is nice, right? This same sampling pattern can be stratified in so many different ways. That's all well and good. But looking at these samples, how will we assess the error? Can you think of a way to take these samples and know how much error there is in integration? Is it a good set of samples or not? Of course, you can calculate discrepancy, and if the discrepancy is low, then it must be good because of the theorem. But is there any other way to assess these set of samples? The other thing you could do is like what you did in the lab. You can take some f of x, you can integrate it with this, and see if the convergence is good, how the error is, and so on. But that requires you to take an integrand. And then you need to take many integrands, see how it does over different things. So it's not very easy to look at this, take a set of samples and assess whether this set of samples is good or not. And one way you could do it is you calculate discrepancy. Any other ways you can think of? Even intuitively, let's say you're in a company and you have some strategy that's generating samples for some application. Very quickly, how will you assess whether this is good or bad? Huh? Okay, you plot it and you visualize. Yeah, that's fairly good. So would you say this set of samples is good or bad? Let me flip through the other ones. Yeah, so between these two, just look at the left. Which is better? It's quite hard, right? Some very obvious cases you will know. And also remember, when you plot it, you only see one instance. So it may be interesting to find a visualization tool where you can take multiple instances and have a visualization that gives you something. Because getting measures for these is not that easy. But yeah, so visually inspecting them is not a great idea, because if you have many realizations, you lose track of what happens, right? So one way people do this is they superimpose this with the points in a different color for a different realization, but very quickly it gets messy. Okay. Yeah. When you do visualization, right? But the problem is, first you need to know in this space what good means. So any mapping you do means you need to understand the mapping. It's the same for geometry, sampling, whatever. So these people will do this if somebody here tells them this spectrum is good or that spectrum. There's no point transforming it into a space where you don't know anything. So that's an interesting point. So what the visualization people, it's a good sort of segue into what I wanted to say. What the Viz community thought was maybe we find some tool to map this into, and then people can look at it there. And this was very useful in reconstruction. People looked at the spectrum. So now instead of looking at the samples here, you look at the spectrum here, right? You can see distinctly there's a difference. And one of them has sort of a blurry ramp up, and the other one has a sharp ramp. And then you can make some conclusions about whether it's good or not. And if you see just random sampling is very obvious. It's not great. Slightly better way. But then this is all useful only if you know how to go from here to making the assessment of whether the sampling pattern is good or bad, right? And for reconstruction, people knew that. Now, what we're going to look at today is how can we do this for integration. We've been discussing a lot about reconstruction and how it's useful. So the question, relatively easily stated, is we have different spectra. We are able to visualize now. We want to know these spectra, whether they result in good or bad integrators. Okay, that's going to be sort of the goal. So remember, we have three quantities and we will color code them. Anything to do with the integrand, we're going to show in red. Sampling, we already saw, we're going to show in different colors. This additional term now is this sample is radial spectrum. The radial spectrum is what we saw there, the 1D version, right? Very good. So let's get some idea now. We've already looked at this. So in the case of images, as you increase the samples, you get to better and better images. You have noisy images, they get smoother and smoother, and you improve this. And we want to know what happens to this slope. For Monte Carlo, we know that this converges, error converges 1 over n. Interestingly, jittered samples converges. So this was in your homework yesterday, right? Jittered and, oh no, you did Monte Carlo and it wasn't in your homework. So I think this is in your lab today. Okay, so jittered samples converge interestingly, not just, so remember important sampling did not change the convergence, it just reduced error. Interestingly, jittered sampling changes the convergence. And we observe in practice something like minus 1.5. Okay, so that's not bad, but with important sampling we saw that we did not really change the slope. Now let's try to take the spectra, because that's what we visually transform the samples into, and see from the spectra can we make any useful sort of deductions. Let's go back to this spatial domain. You have these spikes, right? In the Fourier domain you get spikes again. This is f of x, this is s hat of omega. The closer these are, the wider these will be. This is all stuff we've seen. Now let's say there's an integrand, f of x. Right. That's the function we want to integrate. That has a spectrum as well. F hat of omega. Let's assume that looks like this. Okay, sampling is just a product. We've seen all this, so I'm going to go a little faster. So it's a convolution in the Fourier domain. All the stuff we've seen. F hat is this orange thing. This is the sampled signal fx times sx. So what happens is you put copies of this at each peak, right? And if they don't intersect, you can simply do a band pass. So for reconstruction, if they were band limited and if these were sufficiently far away, then we can throw away all of these and just keep the central replica. We have perfect reconstruction. So in reconstruction, that is easy. But what happens if your sampling rate is low? If your sampling rate is low, these things move closer and you get aliasing. Summary of what we've done, because we're going to go now from, we're going to jump from this to integration. So again, reconstruction, we want the green spectrum. We're going to chop off here. And if they overlap, we cannot chop off. Now what happens in Monte Carlo integration is, instead of this case, which we don't want, where the orange spectrum intersects the green spectrum, do you remember which part of the Fourier spectrum carries the integral of the function? DC. So if omega equals 0, we saw that f hat gives you integral of f, right? Which means, unlike reconstruction, where we wanted a low-pass filter and remove these, when we integrate, we are only worried about DC. We don't care about this green area. DC of this gives us the integral. So we don't want the orange spectra here, the alias spectra, to intersect DC, but they are very welcome to intersect the green area. which means integration is slightly easier. We don't mind if the aliases intersect, which means that we can sample at slightly longer time periods. Right? So we don't care if they intersect. But if they intersect the DC, then our estimator is going to get polluted. These aliases now, because they intersect DC, will contribute error. Is that clear? So that's the difference between reconstruction and integration in this Fourier domain. And actually, this is, it looks very obvious, right, when you state it like this, because this has been known for decades. And so when we published our paper in 2013, there was only one other paper which had looked at something similar, and that was in 2011. So this jump from reconstruction to integration has taken several decades, almost a century. But actually, it's not such a crazy jump. It's just saying instead of green, we wanted to make sure that is the fundamental idea. Okay? So all the analysis that tells you what the error integration is what happens at DC. What do the alias components contribute to DC? And the reason for that is easy to see, right? So if we have I is this, okay, so let's keep things simple for now. Let's assume it's this. Then we know that the Fourier transform of f of x which is this is nothing but minus infinity to infinity f of x. You should be able to do this in your sleep by now, right? You have something like this. If omega equals 0, then f hat of omega, which is 0, equals minus infinity to infinity f of x dx, which is equal to 1. So the Fourier transform at the DC component is nothing but I. And what we can then say is, what we want to do is not integral. We only have fs of x dx, correct? Where fs equals f of x times s of x, the sample signal. So if we replace it here, then we get integral of f of x, right? This is what we are calculating as mu n. Mu n approximates this. Now, what is the Fourier transform of that? Because it's linear, you can pull it into the integral. So you get, there's a product, so what happens inside? You get a convolution, right? And then remember, this integral takes the DC, correct? So it's actually simply at omega equals 0. So the integral is simply the DC component. That integral outside goes away. Instead, you're saying take the convolution of f and s and look at omega equals 0. Convolution is hard to compute, but it's not hard to compute when omega equals 0. Correct? Because at omega equals 0, it simply becomes a product. So convolution, what we did was we took function A, slid function B across, and we had a whole function. So to get that whole function, which is the convolution, we needed to do the sliding. But if you only want a point sample of the convolved value, which is at DC, you don't actually need to slide. You just need to put it at these 2 points, multiply them, and that's it, right? And integrate that, just one location at DC. So there's no shift. Shift is 0, so it's simply a product. So you can simply write it like this. This is a very important result, because what this tells us is our integration of a sampled function can be represented in the Fourier domain. Is f a random variable? Yes or no? Yes. Is S a random variable? So S is clearly random because we're going to choose random samples for S of x. So S is clearly random. F depends on your perspective. If you want to do this for all functions, then you choose a random function and look at this, then F is random. But if you're given a particular integrand and you want to integrate it, then F is not random, right? However, because S is random, this Fourier transform, this expression, this error, right, that value for the integral is a random variable. So you can think of expectation, variance, and all that stuff. Okay. However, there's some important thing here that we've glossed over, which turns out to be a real pain. Right? In practice, we don't have this infinite domain. And the Fourier transform, all this stuff holds if we have an infinite domain. What do we do if the domain is finite? Any ideas on what we can do? So we are assuming this function is over the infinite domain. But if the only part of the domain we want is 0, 1, how can we do anything with this? Yeah, the easiest solution is you define f rectangle equals f times the box. Okay. And then you do everything after that. There's another way to do this. What is the other way you can solve this? So this is one approach. This is the approach we took in our paper. There was another paper which took a different approach, and that's fine too. So instead of clipping that function, we could also assume that that function was periodic. And you look at it in one time. Okay? There are different approaches. So what happens in this case? In the periodic case. By the way, did you all read up on discrete spectra, all that? Has anyone not read this discrete versus continuous spectrum? Discrete Fourier transforms. All of you have read it. So then you should remember. So I'll just show you one image which I think a lot of people refer to all the time. In fact, I tell my students you should make it your desktop wallpaper, because no, it's discrete. So if you are interested in understanding this stuff, I would say this image sums everything up. Okay, and there's explanation in the SIGGRAPH course notes that I've shared with you about this. Okay, this is the primal, this is the Fourier domain. It's a lovely image because it gives you an idea. So if you have a Gaussian, let's say, or some function like this, infinite domain, your Fourier transform is something like this. Okay, you don't have to worry about the numbers, width, and so on. The shape is something like this. Now, what happens if you have a periodic function? Remember, I just said one way you can do it is just think of the function as being periodic. Then what happens is your Fourier transform becomes discrete, which means you have a Fourier series. So there are only integer frequency values because of this assumption that the function is periodic. Okay? So this is like saying you have an image and you want to blur. Now if you take the first pixel in your image, so let's say you have this image, okay? and you want to blur, so in this case, let's take a low resolution image, 5 by 5 image, and you want to blur this pixel. What would you do? You would put a 3 by 3 kernel here, average all these values, and add that value to the center. That's a convolution. But there is no image here. So you can do two things. You can simply average these three, or you can take these here or here, right? You can rotate, go up either this way or diagonally. So you make these choices. And when you make these choices, you are actually defining how you're going to treat your function. If you only take these three, you are treating your function as though it was clamped, multiplied by a rectangular function, box. If you wrap it around this way, you're done modulo 1 on both, right? If you wrap it around only this way, then you're done. So basically, how you treat your domain mathematically depends on what you're going to do with this in practice as well. Okay, that's the connection. So when people say toroidal domain, right, it can easily throw you off because you're wondering what does a torus have to do with this? But what a toroidal domain simply means is that you have taken the 0, 1, okay, you've wrapped around here, which means if you go off that, you come back. If you go off this, you come back here. In addition, you've taken these two edges. So if I glue these two, then these two are circles. I've taken this around and pasted it again. I can't do it with the sheet of paper, but you can imagine if you take a pipe and twist it around, you get a torus. So actually what's happening here is by virtue of creating this periodicity, you've changed your domain from being 0, 1 to a torus. And the nice thing about the torus is it doesn't have boundaries. And when it doesn't have boundaries, a lot of the analysis becomes easy, your function becomes periodic, and your spectrum becomes discrete. Your spectrum becomes discrete. Okay? So can you prove this really quickly? Can someone give me a 2-line proof for this? It's very easy. If you've understood everything I said yesterday, it should be very easy to prove that this will give you a discrete spectrum. This one, okay? Yeah, that is the interpretation of this. But I'm asking, how can you prove that a periodic function gives you a discrete spectrum? It's very, very easy. Take this. What's the difference between this and how will you go from here to here? What operation do you need to do? Shift? No, it's not just shift. There's many, many peaks. Convolve. Yeah, you need to convolve with a delta train. If you convolve this with a delta train, you get this. What is the convolution in the Fourier domain? Multiplication. The delta train is a delta train in the Fourier domain. So this becomes a multiply this with a delta train. Right? And then you get this. This is just like sampling the delta train, right? So it's very easy to prove these things if you understand what's actually happening. Now, similarly, you can go from here to here. If your function was discrete and sampled, then you multiplied with the delta train, you convolve with the delta train, you get this. Okay? So you shouldn't need to remember this image at all if you understand this. Anything somebody asks you, you simply need to remember this. And then you can work it out very, very quickly you can work this out. So what's happening here? How do you go from here to this? Actually, once you start working this out, the downside is that you forget to actually look at it as a discretely sampled signal. Instead, you look at it as multiplying a continuous signal, right? So that's, but okay, so this is saying that if you have a discretely sampled signal, then the Fourier transform is going to be periodic. Okay, if you have a discretely sampled periodic signal, which is what we have in practice, if you have a toroidal domain and you're sampling your function discretely, like an image, then you have this. Then you have a discretely sampled periodic Fourier transform. Okay, so when you call FFT, some FFT calls will give you this option. Do you want toroidal? Do you want to multiply by a thing? So you should understand that's all it means. So if you give it a periodic option, then the FFT call will give you back this. And Obviously, they don't need to store all of this, so the FFT will only return this. Okay, so that's a very useful image to remember because it tests whether you've understood all the other stuff. Okay, good. Now, why did I come here? Because I was there, yeah. Okay, so now we understand omega equals 0. We understand error contribution to this. And we said if we are in a finite domain, we can treat it two ways. One, we can treat it as periodic. The other, we can treat it as multiplying by runtime. Okay, the key difference is, remember, in reconstruction, we don't want intersection with a green curve, central copy. In this, we don't mind it as long as it doesn't intersect the DC copy. Okay, so there's been several papers after ours as well who do these type of things. And so that's how we get integration in the Fourier domain, right? Because the integral of f of x is simply f hat of 0. This is just summarizing what I wrote. Your estimator, some n sampled estimator mu tilde is this. You take your sampling train. Obviously, these are all random variables. Because xk is a random variable, these things are random variables. And in the Fourier domain, I left out a conjugate there. For real values, it doesn't matter. But in practice, it's the f conjugate with s. Okay. So now we've got all of this stuff. So that is the Monte Carlo estimator in the Fourier domain. And this is relatively new. It's only been known in the last 5 years. Okay. Just remember this. You want to get an estimator, it actually looks very similar to this. The integration variable is in the frequency domain, but you do have just a product of this. Okay, it turns out to be very elegant. And remember that your S hat is nothing but Fourier transform points. And these are the Dirac's in the case. So the question then is, how do you formulate this error? Intuitively, we understand if these things overlap DC, then you need to look at error, right? Simplest thing we can do is we take, Yeah, that's a good question, right? We don't know. That is why I said, if you're given F, then you know F. If you don't know F, then F is a random variable. There's two ways to analyze it. We have not come to that. That's a good. We will see how to treat this, right? So that's a good question. The question is, we know S, but we don't know anything about F. So how can we get there? Simplest thing we can do for error. Remember, this is all looking at the estimator, not the estimator error. If you want the error, you take I minus mu n. So assuming you have I, which we don't, but we just want to know what error looks like. So you're going to simply do this. And then this is really what we want. This is the estimator. We move that up there. We can replace this integral with just the DC term. We rewrite. So this is all stuff we've seen before. And again, remember, that is the error. And in general, we know error is the square of the bias plus variance. You can derive this. It is MSC error, mean squared error. We've seen what bias is. We've seen what variance is. Bias is the shift away from the center. Variance is the spread of your Gaussian. And the MSC is a combination of both. So we have two different components of error for integration. When we do reconstruction, we don't necessarily have these obvious components. We just have MSC usually, right? And of course, bias is nothing but the expected value of the error. So you subtract this random variable from I and you take its expectation, you get bias. If it is unbiased, you get 0 as the expectation. We looked at this as well yesterday. The variance is nothing but take the difference and you calculate the variance. Right? Remember again, mu is a random variable, I minus mu is a random variable. You can take expectation as well as variance. Now just let's look only at bias. Okay, so when you do I minus mu n, I is f hat of 0. So you get this, right? And then you subtract it. When you take an expectation, this is a constant. If you know the function, then f hat is a constant. So there's no expectation operator there. The expectation operator is only here, right? And you can simply take the expectation operator inside the integral. It's all linear. Okay? You take the expectation operator inside. Again, we're working under the assumption that f is not varying. It's not random. It's not stochastic. So there's no point in keeping this inside the expectation. So we move the expectation to the sampling. So that's really the key contribution in this paper or in this result, is that to look at the bias of an estimator. All we need to do is to look at the expected sampling spectrum. Notice there is no amplitude here. It's a complex value. All the while we looked at the sampling patterns, I was showing the amplitude of the power spectrum. I was showing the power spectrum, which only looks at the amplitude. This one looks at the amplitude itself. This one looks at the spectrum itself in expectation. So what should you do? If you want an unbiased estimator from this equation, can someone guess what we need the sampling pattern to satisfy? If you want the bias to be 0, what should the green box return? It should return f hat of 0. Then this becomes 0. To get f, this already has f hat inside. So what should s be to get 0, to get f hat of 0 here? If s is 1, then you get integral of f. That's not the same as f hat of 0. Remember, this also is a hat. This also has a hat. So we want this to be f hat of 0. We've seen this yesterday. You should be able to tell me, right? So let's, if it's not immediately obvious, right? So we had f hat of 0 minus integral f hat conjugate of omega expected s of omega d omega. What should this be for this to be f hat of 0? Yeah. So if this was a Dirac, then what happens when you have a Dirac? You take its peak at 0, then you take f hat of 0, the rest of the integral vanishes, and you get f hat of 0. Okay. Oops. So if the expected sampling spectrum is a Dirac at 0, then we are done. We can prove that it's biased. So now, in contrast to the low discrepancy sequences, where we said as long as your discrepancy is low, you can be guaranteed, regardless of what integrand you put in, you get unbiased, or you get low error. We are saying regardless of anything else, if your sampling pattern satisfies this, you get 0 bias. Right? This is a Dirac. That's an interesting result, which means that you can come up with any sampling pattern you want. Just make sure that it's satisfied and you don't have to worry about bias. Proving biasness is very difficult. So for example, Sunil suggested, we can take jittered sampling, reduce the size of the box. To prove that it's unbiased in that particular case, to prove that it's biased is not very difficult. You can argue, look at this part of the domain, you never get a sample. But in general, proving something is unbiased is not easy. However, looking at its spectrum and doing analysis there may be easier, especially if it's just identifying if it's a Dirac. So if you derive some Fourier sampling spectrum for your sampling pattern, you don't need to worry about the complicated expression. Just look at, is there energy outside DC? Yes, then it doesn't satisfy this. That doesn't mean it's biased, but it's not obvious that it's unbiased. Whereas if it satisfies this, then it doesn't matter what else, you can say this is biased, unbiased. Okay. But the question is then, how do we get this? How can we get a sampling spectrum where only DC is non-zero? Remember that this is amplitude and phase. So this expected spectrum has an amplitude and it has a phase component. Right? This phase component. This is no longer the base radical inversion. Okay, sorry, it's the same thing, but this is now the phase. So you have amplitude times phase for this expected value, and you can't take the amplitude inside the expectation. Reason is we saw yesterday, if your points are on the circle, each of them has the same amplitude, but when you add them, you get a different amplitude. If you take this inside, then you won't see that. Okay, so that's your amplitude and that's your phase. Now let's look at a regular grid. Okay, take a particular frequency, omega. Okay, we take one particular value of omega, take each of these samples. Okay, you will have some phase, and people have looked at a lot of different things. Okay, now if I take a regular grid, here is another idea. I take a regular grid, but I don't like the structure because it creates this banding. So I will offset it every time. I will draw a random number, and I'll simply offset the regular grid. That seems like a pretty cool idea because that guarantees that I will reach every part of the domain, and I can use the same regular grid every time. I only draw one random number. So it's very quick. It's very fast. And can we analyze this? The regular grid itself was biased. It's very obvious it's biased because there's so many parts of the domain where you never get a sample. Now, is this unbiased? It looks like it could be unbiased, right? Intuitively, it seems like it should be unbiased. Can we prove this? So one way, maybe let's see if this new result helps us. If you think that this regular grid gives you some amplitude and phase, like there, when you shift it, you're just going to move that in phase. And so different realizations will give you different shifts, right? So for a given omega, if you've randomly shifted it, then you're equally likely to go in any of these directions on the phase. So it could be anywhere on the circle. So in expectation, what is the phase? So it's going to make all energy cancel off for every omega. So for any omega, so this was all for one omega, right, this circle. Regardless of the omega you take, you can show that there's uniform distribution over the circle because of your random shift. Your random number is uniform, shift is uniform, so phase is uniform, which means the phase will cancel off all the amplitudes at every frequency, except omega equals 0, where you don't have phase, it's just integral. Okay, so that is sort of a neat result where we can show that by taking a regular grid and shifting it randomly. As I said, this is not something we did. People have been using this since 2000. People identified that you can take a regular grid and shift it around. But the analysis of that was done by intuition. People said, oh, look, it's a regular grid. If you have one grid, it's unbiased when you shift it. When you have multiple grid points, it should simply be the same, right? So you can prove it somewhat mathematically as well. But it was quite neat here that we could show that in the case of the uniform grid, for all omega not equal to 0, this is 0, and therefore it must be unbiased. Okay, so that is the bias term we've looked at for so long. Okay, and this process of performing a random shift, you can do it to any pattern. Any sampling strategy you get, you can always shift the entire set of points by a constant offset. And if points go outside the domain, what do? Wrap it around as a toroidal domain. And it can be shown that this holds for any sampling pattern. So you can take a Halton sequence, you can take a Hammersley sequence, you can take Jittered, you can take random. Anything that we've seen or anything else, and you shift it, you will satisfy this criteria. This is interesting because now we're saying if you take a biased sampling pattern and shift it randomly, you get an unbiased sampling pattern. Okay, what's the downside? What's the problem with just shifting any sampling pattern? There's a problem. It's a very obvious problem. Why is the number of samples changing? Yeah, but that we do with anything, right? So you're going to use multiple realizations anyway. So what is the problem with just simply shifting? It seems ideal. We just generate, one 2D random number, shift it, and we're done. Problem is, whatever nice properties these samples had, I don't know if that's what you're trying to say, is if these samples had nice properties for example, stratification, for example, all these discrepancy and all that stuff, we may lose them because of the random shift. Because when you do this modulo thing, it comes on this side, we don't know if we can guarantee it anymore. Right? So it's hard to prove that they do, but in fact, you find that actually it does. So the cost of removing bias is adding variance. It is almost always observed that when you try to decrease bias, there will be a decrease in variance. So it's sort of this uncertainty principle, right? It's connected to the uncertainty principle. You cannot have zero variance and zero bias. So these two are related. Okay. Questions? Okay. So there we've seen how we deal with bias. So now the obvious question is, okay, by doing all this stuff, what happens to variance? So there is no point studying an estimator only for bias. Unless you're in, for example, tumor detection, you want to run this algorithm, you have a supercomputer, you just run it for millions of samples. You want to make sure that when you do that, there is no error in the expectation. Right? Then bias is the only important thing, because variance then gets marginalized by compute power, number of samples, and so on. In practice, it's not that simple, because your variance is large. You don't know if what you're seeing is just variance or not. So in theory, you want an unbiased estimator, but in practice, it's important that you have some idea. So this process is called homogenization, because what you're doing is taking a set of samples and making them homogeneous in the domain by doing these random shifts. Homogenization decreases bias, removes bias, adds variance. There's another problem with homogenization. Can someone see it? It's related to your lab yesterday. If the samples were not uniformly distributed, doing this random shift will make the distribution uniform. So for example, if you're doing importance sampling, and you take your importance samples, which let's say you had a Gaussian importance function, you had more samples in the middle. You perform a random shift, then the next set of samples, the Gaussian will move here, first, so next set here, next set here. So on average, you will sample all parts of the domain uniformly. So you lose this advantage of importance sampling by homogenizing this. Okay? So there are two drawbacks, but still it's quite useful in practice. Okay, so that's, however, the advantage is now we can only study variance. So if you're given some arbitrary sampler, like Halton, right? You look at the Halton sampler, it seems, first of all, if you look, remember the construction of the Halton sampler, you had this base 2, base 3, prime bases, and you had multiple dimensions. So any proof you want to do for Halton sequences, you need to be an expert in number theory, right? Because that's what you need, relative primes. You need to look at these radical inverses. So you need to understand that mathematical toolkit to make any analysis. What we are hoping is that if you do this with Fourier, we don't care that you've used a radical inverse, you've done all this stuff. We're just going to Fourier transform it and understand it. Okay? However, if you want to get the analytical Fourier transform, either you need to understand that, or you simply take the samples and then compute the analytical, which is what you'll do in the lab today. Okay, so the advantage is now we don't understand anything about number theory. We don't understand all these radical inverses and all that stuff. So we will just try to look at it in the Fourier domain. But what if that is biased? Because I can't prove it's unbiased if I don't understand number theory. So what I'm going to do first is take whatever it gives me, blindly shift it by a random value. Then whether it was biased or not, now I know it's not biased. Then I'll look at its variance, right? So if you give me 10 estimators, 10 sampling algorithms, what I'll do is I'll take each of them, apply a random shift. I go into this new space of homogenized samples corresponding to each of those. Then I look at the homogenized samples to see if the variance is compared. Because I know they're not biased anymore, I'll see which one has higher. So I can shift my analysis from bias to variance by homogenizing at the cost of not being able to importance sample and losing maybe some structure. Okay. It's 12:23, but no one's signaled me for lunch. So rather than wait outside, I think we should continue. Unless you want a break. Okay, so now we look at variance in the Fourier domain. We'll go back to this equation. How did we do bias? We took expectation there and we pushed it in. Instead, we take the variance operator there. What is the variance of f hat of 0? 0. It's a constant. Take the variance here. Okay. I'm going to move the variance here. Now, the variance of the estimator is simply the variance of this. What is the variance over a summation or an integral? Can we take it inside the integration operator? There is no problem. Right? But remember, unlike expectation, where we simply took the expectation of S hat, now when you take the expectation and move F hat out, you need to square it. Right? Because the variance of a constant times x is k squared times the variance of x. Because variance is a squared second order measure of dispersion, right? So basically now we have to, because of that, square this. What happens when you square the Fourier spectrum and you have this conjugate here? You end up with the power spectrum, square of the amplitude. So there's the nice thing now is the phase of this has gone away. Right? We don't care about the phase. In the previous case, we had phase of both. Now this has gone away and we have variance of the sampling spectrum. So that's the variance of this estimate. Okay. This is nice, right? It's again an elegant form of the variance. We're saying we have some estimator. The variance of this estimator, if you want to understand it, just look at the variance of your sampling spectrum. To understand bias of the estimator, we looked at the expected sampling spectrum. To understand variance, we look at the variance of the sampling spectrum. And this is a general form. It doesn't matter whether you homogenize, non-homogenize, any set of samples. That is the form. Okay. So what happens for purely random samples? What would this be? Variance of S hat omega. We can derive that. The variance, this was just the power spectrum of S hat. Because the phases are random, you can make certain simplifications. Okay. So actually, this is quite a strange thing. So Fredo Durand, who was my PhD co-supervisor, he made certain observations of this. So we both started studying it at around a similar time. He had made, in a tech report, he had made certain observations of this and laid down some of the stuff. But he had not actually published it. And interestingly, he did not present the variance and bias form, which would have been obvious at that time, but it wasn't. Anyway, so that was published a couple of years before we published the other result. And in his work, he simplified this variance term so that, again, it's funny because he didn't recognize this term, but for the specific case of random samples, he had shown this. Okay. Yeah, so for purely random samples, we know the expectation of S hat is 0, right? And we know that homogenizing gives you this except at DC, right? So we can also write that the variance is in this form, the inner product of the power spectrum of the integrand and the expected power spectrum of the sampling sample. This again, some postdoc proved this subsequently in 2015. So there were two first authors. One was Gurpreet Singh and the other one was Adrian. Anyway, so these two guys said, okay, we will take this further. We will look at homogenized samples. All of the error, right, we saw variance, bias, we have understood now, except what have we not understood. There's one thing we still don't understand. Or we don't have a formulation, which is this convergence. We have not seen what happens to the slope. None of this Fourier theory tells you anything about convergence. So these guys said, oh, we want to analyze convergence, but before that, let's see what these spectra mean, right? So they took two similarly distributed points, arranged points. They're all uniform, but slightly different spectra. And you can see the difference in the spectra is here, mainly. This one is non-zero, this one is 0. Again, the power spectra looks similar. So these are the expected power spectra. And look, that's what's in the variance. So what this is saying is, if you take the power spectrum of your integrand and take the inner product, that means if you had an image of the integrand and you do pixel by pixel multiplication and then average, then you will know what the variance is. That's in practical terms what this equation means. Okay, so what they did was they wanted to study this in polar coordinates, right? So you remember this integration. So all this pixel by pixel multiplication is in the 2D domain. Nothing we can derive from here. So they said, oh, this is a real pain because we have to do all these integrations. So they said, let's see what we can do in polar coordinates because then we can do these integrations and so on. So I won't delve into the details of these things, but they ended up showing for isotropic power spectra. So imagine if this was not a circle but an ellipse. This can happen for certain sampling strategies. Then when you integrate in circles, you'll see this bizarre sort of shift right on each integral. So they said we don't consider those spectra. We assume that this, if the spectrum is isotropic, which means it is rotation invariant. Doesn't matter how much you rotate the spectrum around DC, on expectation, you should get the same spectrum. Those are isotropic power spectra. Then you can talk about integrals over these curves, and then you can take the polar representation. You can sort of work through this. There's the reference to the paper and the slides are there, so I really won't go into the detail. And they came up with this. They said the variance is, so some measure here times the power spectra. So they showed that this is also true if you look at the 1D. That's important because if you are visualizing this and analyzing this, we need to have some idea of how this can be interpreted in terms of error. And they showed that you can actually interpret the error from just these two. That's good news because from a visualization perspective, now we can do away with all of these things and simply look at these two curves. 1D curves, easy to interpret, and so on. Okay, so there we have the power spectrum. Again, sampling spectrum. Okay, so rho is this radius going out. Any questions? No. No? Okay, so now let's look at the what these power spectrum is. So let's say the integrand's radial power spectrum is like this. So it has a lot of energy in low frequencies. This is the sampling radial spectrum. Remember, this is the inner product, right? So if you take the inner product, even though the integrand is high, because this is low, the contribution will be 0. And you'll get this. This is the inner product of the two. This green curve. What does that tell you? That tells you that the variance is this is the product and the inner product is the area, this green shaded area. So if that area is large, it tells you that you're going to have high variance. Okay? So now if you have performed your homogenization by randomly shifting your samples, then you can forget about bias. Simply look at this green curve for any two sampling spectra. If the area of one looks larger, then that is the one that is higher variance. So now we've gone from sampling to spectra to radial to error after product. Okay? And all this stuff that I told you was just the proof of why you can do it. And here's another case. If your sampling spectrum is far out, then the green curve looks like this. And it's non-trivial to look at these green curves and say which one has larger area. But hopefully, if you have these in some representation, you can actually calculate that or numerically estimate. function of omega. Well, the variance depends on the integral only, right? So if you look at this equation, we don't know what it means for the variance to be very high at one frequency or not, because there's no notion of what is the max and so on here. So we don't probably care about where the mode is or what the mode is, what the value at the mode is. Maybe there's a result, but we don't know. At this point, all we know, when I say at this point, not just in the lecture, also in reality, we don't really know anything more yet. Okay, so that 2015 paper, they did this 1D thing, and we know now that the integral matters. There's another thing that matters, which I'll mention. So if you take this sampling spectrum, unlike reconstruction, where you can easily look at it and say something, it's very hard in this case because we really care about the area under this curve. That's all we have in this result. And whether this sampling is better or this sampling is better, your guess is as good as mine, right? And you can see here, because there is a low frequency area here, it's kind of low here, the product, and therefore you hope the area will be low. However, what happens if the integrand has a massive spike here? Then this actually, even though we said so far that we want the sampling pattern to have low frequencies, what we didn't say was if the sampling pattern has a spike here and the integrand has a massive spike there, that would be the worst sampling pattern to choose. Okay, so in some sense, if you don't know the integrand, we can say something, but if you know the integrand, best thing to do is look at both the spectra and see. So if you're in a practical application where you kind of have a prior on the integrand, or you know exactly what the nature of the integrand. So in many cases, you may not know the function f, but you may know spectral properties. So if you're in signal processing or in image processing, if you see an image which is pretty low frequency, like smooth, then you know that most of the energy is in the low frequency area, intuitively. And you can even calculate that by doing FFT and so on. So this is more for specialist analysis than for actually algorithmically computing at this point. Hopefully that will change. Okay, so that's one thing. Clearly, increasing this and making it, pushing the energy to the high energies is a good idea when the integrand is here. So in practice, actually what we want to do is we want this spectrum to complement the red spectrum. If you have the red doing this, then you want the blue one to be out of phase with that, doing something similar, doing anything in the middle, but not peaking at those. And so when we came up with the 2013 paper, we were hoping that the next paper published by anyone would be an optimized sampling pattern where you take an integrand, look at its peaks in the spectrum, come up with a sampling pattern that has peaks offset from it so that you get low variance. It turns out that's quite hard. So far, no one's done it. And we've tried it as well, and there's a lot of optimization issues. But it seems like that's the main benefit of knowing this. Okay, so yeah, again, that's the way. So in general, if you take two strategies and you don't know anything about the integrand, you look at these two curves and straight away you see this one goes far out, low energy here. This one only goes till here. However, as you go closer to zero, this one actually goes to zero, this one's constant. So if all the energy of your integrand was very close to DC, maybe you would choose this over this. Okay? And also you see this has a sort of a flat frequency agnostic behavior outside this. Whereas this has these bumps. So if you know your integrand may have peaks here, then maybe you don't want to choose this. Yeah, so I mean, they did a lot of analysis and they found some worst case and best case bounds and so on. So the advantage of now homogenizing is that they could only study variance, and then they looked at what happens to these particular sampling patterns that are used. And they looked at all of this stuff. Okay. Yeah. So if you look here, these two, jitter and Poisson disk, two different sampling strategies. If you look at the worst case, this one's better. Converges faster. If you look at the best case as well, this one is better. Okay. But if you look at the spectrum, right, maybe it's coming up soon. It's not obvious here. So here's the spectrum between jitter and Poisson disk. It's very strange that the convergence rate has changed for very similar spectra. So these observations we made of not going to zero, pushing out farther, these bumps, somehow they are tied to convergence rate. Apart from variance and bias, there's some clues there that you can consider all these parameters and maybe understand convergence rate. So if you zoom very close to the origin, this is what it looks like in both the cases. So if you look at what happens to the product of some arbitrary integrand, the green is again the product, right? So as you increase the number of samples, what will happen to this blue curve? Can someone guess? So this is for a particular n. If you increase n, what happens to this blue curve? Will it go higher? Will it change shape? Remember, this is the frequency domain representation of a fixed set of samples. If I increase the sample, so let's take a Dirac delta, and you increase the number of Dirac deltas in the domain, fixed domain. Instead of 10, you put 50. What happens to the spectrum? I know all of you know this, but you're not telling me. We've said this many times, right? So this is your spectrum, right, for 4. Now this is your sampling pattern for 4. Now I do 8. Okay, the Fourier transform of this is something that looks the same, right? What would the Fourier transform of this be? How would it compare to this? Will it be the same? Will it be wider or will it be narrow? Wider, right? So this is going to spread out. So you will lose this, so it will become nice and wide. So when you squeeze things here, it widens things there. So as you increase n, the same thing should happen to the stochastic samples. This curve will just get pushed out to higher frequency. Similarly, this curve will get pushed out. Now intuitively, can you tell me, increasing n is nothing but in our convergence plot, where we showed this slope. On the x-axis, we had log n. Increasing n means you're going there, along that axis. What's happening to the y is what we want to know, the error. Now, looking at this intuitively, can you tell me what would happen if you keep shifting the spectrum to the right? This will keep shifting. The integrand has not changed. Only the sampling pattern is changing. So the green curve will start moving. And if this is 0, in the limit, when n is really far away, because it goes to 0, what would happen? It will be very low. Correct? However, in this case, because you have a constant here, regardless of how far you push this, there is always going to be this residual thing, even at n. So that gives you clues about convergence. So that's one of the clues we have. So as you increase the sampling count, this converges better than this. So we don't have analytical results for this, but we understand a lot of the stuff with this. This is all observed, yeah. So some of them they're proven, but this is observed, yes. And also you can calculate these for average random F. So you can do expected. So what they did there was they took worst and best. So they said if you have the worst function possible, what is the convergence? If you have the best function possible, what is the convergence? And look, and for Poisson disk, it turns out that whether you have best or worst, you are at Monte Carlo. It's not better. So you have not improved the convergence by doing Poisson disk. Whereas Poisson disk samples look really amazing. And if you remember, the monkey's eye had Poisson disk sampling. Okay, so monkeys, what does that tell you? Monkeys have evolved to the ultimate point possible for signal reconstruction, but they are not at all evolved for signal integration. They don't care about what the integral of the energy is. They only care about what is the distribution of the energy, what is the reconstructancy. Right? So it would be interesting to see animals where they cannot process multiple bits, but they have multiple sensors. So for example, ants, in their brains are so small that actually the neurological circuitry in the brain is now mapped. There's one person, the head of our department, works in this, and you can see that they have a map. They know exactly what the wiring is in the brain. They don't have that many bits to deal with. Okay, but they have many sensors. Their compound eyes have a lot of elements. So an interesting thing to study, I don't know if anyone has done this, would be to see if they have evolved some mechanism where for integration they do so. Because there are few bits in the end. Yeah, so anyway, so that answers your question, right? So you look at the best and worst case, and then you say, okay, somehow we know that in the worst case or in the best case, this doesn't change, whereas this changes. So this is also quite satisfying. And of course, you can verify the convergence rates. And if you look at, this is the integrand, 0 and 1, or maybe it's some low value, 0.1 or something, and 1. And then the simulation basically tries to integrate this. It's not integrate. So if it's 0 and 1, then you're getting the area of the circle. If this is some 0.5, then you're getting something else. And by using different sampling algorithms, this is Monte Carlo and this is variance. So this is Monte Carlo variance just with random sampling. These are the different samplers. So if the disk is the worst case, right? This is the Gaussian is the best case. You can see that the sampler is spread out a lot. This is quite interesting. Normally in complexity theory, computer science, in many of these analyses, people use worst case, okay? Because you want to be conservative. In the worst case, they are actually not very far apart. All these different algorithms from something that is 40 years old, 30, 20, 25, 30 years old, to 5 and to 7 years. All of these algorithms for the worst case are not that different. Of course, there's some slightly better ones. However, if you take a nice case, like a Gaussian or something like that, suddenly there's a huge advantage to using some of the newer methods. And in practice, whatever application you're doing, you may find that in many cases, you have this smooth case, and you can benefit from an algorithm that does very well in that case. So this is a classic example of looking at worst case and losing out. So a lot of people will look at the worst case and say, oh, it doesn't matter, let's just pick one, right? And in this case, it happens to be that for worst case, blue is better, but it need not be. And so basically, you need to choose the sampling algorithm that works for you in your application, given the data. So in this case, if you take the extreme example of a super smooth function like a Gaussian, turns out that the benefit to be gained is huge. What does this tell us? This tells us that if you account for the integrand and its smoothness and all of that stuff, there is a lot of work to be done and sampling can be improved a lot. So here are some examples. I think, so again, this tells you, compares the different sampling algorithms and so on. And in practice, so this is now integration in the space of photon integration that I talked about over the hemisphere and all that stuff. In that case, for that high dimensional integration, you get this. Okay. So you see that two algorithms here are pretty good. These two, depending on where you are, can be good or not. And after a point, blue is better. So Jittered and Poisson disk. Jittered has higher convergence. We already saw Poisson disk is same as Monte Carlo. So if you're using lower than, in this case, some 200 and something samples, then you probably want to use Poisson disk. Later, you don't. And again, it's very specific to the same thing, right? So okay, we've seen a lot of stuff, and still nobody has signaled for lunch. So by 12:40, so we can break. Okay, so we'll maybe look at this tomorrow. Then we can break for lunch. No, also I mean, it's been an hour and a half, right? It's a long time. Okay, so maybe what I could do is I could use this time to, so you probably already have a lot of ideas of what the benefit is. I've been mentioning it all along. Now maybe we can look at what is your lab exercise. So you've done homework 2. Okay. Today will be L5 and L6. So in your lab today,